Thanks again for coming to join us. I'm Rob Armstrong with Brady Train Sales, and got a few quick reminders for you. We do have PDH credits available after this session. You can find them in the back of the room as you make your way out. Also, we do have our expo going on right next door, so make sure and check it out on the latest and greatest of the HVAC technologies. I will be introducing our local John Roberts. John Roberts will be talking about the 2012 Energy Conservation Code. He'll be targeting the major updates and explaining the special new features. John Roberts has a Bachelor's of Science in Mechanical Engineering from Cornell, a Master's of Science Public Health from UNC Chapel Hill, and John started his career in private engineering work with the Department of Energy, specializing in schools, hospitals, and energy conservation projects. John now has 30 years experience in mechanical engineering design and continues to focus on hospitals and green building design. John currently works for Dewberry Engineers in Chapel Hill, North Carolina. He has a professional engineering degree. He's a lead BD+C and healthcare facility design professional. Most notably, he is a member of the NC Energy Ad Hoc Committee. This committee reviews code changes for NC Energy Conservation Code, which he will be speaking about. So without further ado, here's Mr. John Roberts. Please give him a warm welcome. Thank you.
Thank you, Rob. I'm glad to be here today. And we are going to be talking about the 2012 North Carolina Energy Conservation Code. We're going to be talking about the differences between the 2012 code and the 2009 code, how this came to be, what the impact on design is going to be for engineers, architects, and others. Just like to say, this presentation just represents my own opinion of the things in the code. I'm not representing the opinions of Dewberry Engineers or the North Carolina Code Council. And, all right. Okay, North Carolina decided to create a code that's 30% more efficient than the 2009 Energy Code. This affected both the residential and commercial codes. Now today we're only going to talk about the commercial energy code, which is Chapter 5 in the 2012 Energy Code book. There were many changes and upgrades from the 2009 North Carolina Energy Code to the 2012 Code. These changes were caused both by changes in the International Building Code as well as specific changes to the North Carolina Code. The North Carolina Code is all on a 3-year cycle. You had a 2009 code, now you have a 2012 code. The International Building Code is on a 3-year cycle, and basically North Carolina lags 3 years behind. So our 2009 Energy Code was based on the 2006 International Energy Conservation Code, and now our 2012 Code is based on the 2009 International Conservation Code. So there were quite a bit of changes even in the International Building Code in that 3-year cycle, plus the specific changes that North Carolina did. Some people who contributed to the North Carolina portions of the code changes were Jeff Tiller with the Technology and Environmental Design Department at Appalachian State University, and Chris Mathis with Mathis Consulting Company in Asheville. And those were contributors to the writing of the North Carolina specific amendments to the code. They're not contributors to this presentation. All these code changes, the International Building Code change and the North Carolina specific changes, were submitted to the Energy Ad Hoc Committee, of which I was a member. So the Ad Hoc Committee reviewed those proposed changes, made some modifications and changes, and then went on to approve that and submit it to the North Carolina Code Council. So the purpose of this code is to save energy, reduce pollution. We know the buildings use quite a bit of energy, and with this code change where we're trying to make one jump and get 30% more efficient, it's like going from this to this. We're really trying to make super efficient buildings now, and I think this is going to be a trend that we're going to keep seeing. The codes getting tougher and tougher, and really being very tough on the energy use. So, the major changes were in almost every aspect: the architectural, the electrical, the mechanical. You have significant increase in building insulation. You have significant reductions in lighting wattage, both interior and exterior. You have the requirement for economizers now in most air conditioning systems. You have the requirement for demand-controlled ventilation. You have fan power limitation. You have requirement for occupancy sensors for lighting in many rooms. And you have the 6 additional optional compliance paths in Section 506 of the Code, which we'll talk a little bit more about later. On this slide, and throughout some of the slides, I've tried to put which changes were due to changes in the IBC, the International Building Code, which were changes specific from the North Carolina revisions. Now, one big difference that we have overall in our new energy code is that in the 2009 code, it was prescriptive. You could use the prescriptive items in Chapter 5 and just go through, and if you comply with those items, then you comply with the code. You still had the alternative path, and you could use the prescriptive requirements in ASHRAE 90.1-2004. So you really had 2 overall paths you could follow, and they were both prescriptive, but you didn't have to do any energy modeling. Now, in our new code, you still have, again, the Chapter 5 prescriptive, so you can still follow the prescriptive code. But now, if you don't want to use Chapter 5 in the code book, your alternative is you can go to ASHRAE 90.1-2007, but you have to do an energy model. It would have to be 20% less energy than required by ASHRAE 90.1-2007. So you're a little bit stuck now. If you want to stick to prescriptive and not have to do energy model, you're just going to have to go through Chapter 5 and you're going to have to comply with it. North Carolina's 3 climate zones. And we have the Zone 3A is the eastern and southern counties. So that includes cities like Wilmington, Renewable, Charlotte. Then Zone 4A is the northern and western counties. That includes Raleigh, Greensboro, Asheville. And then we do have Zone 5A, which is only the mountain counties in far northwest, so you have Boone up there. Note that these zones are Zone 3A, 4A, and 5A. There are zones 3, 4, 5, B, and C in other parts of the country, but we don't have any of those in North Carolina. But that has a bearing that we'll talk about later. Okay, so first we're going to talk about the envelope requirements. And the envelope requirements have been substantially increased from 2009 to 2012. You see that in 2009, your basic requirements for a metal stud wall and exterior wall was R13. Was R13 for zones 3 and 4, where most of us work. And now, in 2012, you can still put the R13 bat in the metal stud wall, but you have to have continuous rigid insulation in addition to that. So either 7.5 continuous for zone 3 or R10 for zone 4. So this is way more insulation. I mean, your R13 is a 3.5-inch fiberglass bat, and in a metal stud wall, this would only work out to actually net about R6. So really, by requiring this additional rigid insulation on the exterior, you're more than doubling the R value of that wall. And of course, the big increase in Zone 5 as well. Now, if you're a flat roof, again, very big jump in insulation. You see for Zone 4 that you're going from R15 to R30, so you double the insulation in your flat roof. The window U values also got substantially tougher. All three zones, the U value went down quite a bit. And the solar heat gain coefficient. Now, the solar heat gain coefficient actually did not change for zones 3 and 5, but a big jump for zone 4 went from 0.4 down to 0.25 solar heat gain coefficient. Of course, that's the amount of heat that gets through your exterior windows, so it's almost cutting it in half for zone 4.
John, question? So is that for just the prescriptive, or is that like a prerequisite, what you just showed?
This is prescriptive, so this is a requirement that you have to comply with on all your buildings unless you want to do an energy model. So we see that overall your impact on your HVAC, on your air conditioning, will be quite a bit, because really your requirements for the envelope resistance to heat gain or heat loss and the solar gain to the windows is just about doubled. So you're pretty much going to cut in half all your envelope heating loads. Okay, now we'll talk about lighting, and also very substantial changes here. The 2009 North Carolina Energy Code only had categories for entire buildings. It didn't have a really big table. It was just a list of building types. The 2012 code breaks down and gives you a lot more options for each individual space. So you can do space by space method, or you can still do an overall building method for your lighting watts per square foot. But you can see that for an office, we had 1 watt per square foot in 2009. Now we're down to 0.89 watts per square foot for an office building. If you go with the optional section 506, then you have to save another 10%, so you're down quite a bit more. And I remember it wasn't too long ago when our lighting code in North Carolina was 2.5 watts per square foot. Now we're down to basically 1 watt per square foot. Even in a hospital, we're maybe down to 0.95 watts per square foot if you take the optional compliance spec. So again, tremendous difference in your air conditioning load, because your lighting watts is going way down from what it used to be. We also now have occupancy sensors are required in many types of rooms, classrooms, conference rooms, break rooms, private offices. So all those now require occupancy sensors. Your exterior lighting watts have also gone down. 2009, your parking. Excuse me?
Can you go back to slide 6?
Sure, go back to slide. Sure. Okay. Your exterior lighting watts, your parking lots were 0.15 watts per square foot. The International Building Code has now changed the system where now you have different zones, and the zones are based on, there's 4 zones, and they're based on, like Zone 1 is a rural, like a national park type area. Zone 4 is a downtown urban area. Most people are probably in Zone 3, kind of commercial area. So you have different watts per square foot you're allowed for the parking lots. based on which one of those lighting zones you're in. But for parking lots, they've all been reduced, so even if you're in the downtown area, you're still down 41.3 watts per square foot. And similarly, walkways and canopies, those have been reduced in your allowable lighting lots. Okay, jumping to mechanical, your pipe insulation, the International Building Code changed that, and they went, on your smaller pipes, your 1.5 inch pipes and below, they've now gone to 1.5 inch insulation thickness on the pipes. So, doesn't matter hot water, steam, chill water, refrigerant, you're now at a minimum of 1.5 inch thick insulation. So even if you have a 1/2 inch pipe, you're going to put 1.5 inch insulation on it. So you can imagine you got a 1/2 inch pipe, you got 3.5 inches worth of, outside diameter on that thing. Okay, we're going to talk about cooling equipment, and all these have changed. Your air conditioning units, chillers. Your air conditioning units, for example, if you have a 10-ton air conditioning unit, 2009 was 10.3 EER. Now in 2012, it's 11.2 EER. And if you go with the optional Section 506, you're up to a 12 energy efficiency ratio. By the way, I think the slide presentation is available for those who are interested in getting it. And I've tried to make these tables and these things together so that you can get the information. I know it's a lot to absorb. Also tried to normalize it to KW per ton, or some of the codes, some of it's been COP, some of it's been EER, some of it's been KW per ton. Okay, your air-cooled chiller, some of those have gone down. If you're less than 150 tons, it's still 1.25 kW per ton. But if you're over 150 tons, that's going down from 1.41 kW per ton to 1.25. And if you do the optional Section 5, it's Section 506, it's 1.2 kW per ton. Then your positive displacement chillers, they've also gone down. If you have, say, for example, you have a 200 ton, then we're looking at a full load of 2009 was 0.718 kW per ton. Now we're down to 0.68 kW per ton. If you go the optional route for a high efficiency HVAC system, then you're down to 0.61 kW per ton. Water cooled chiller, also going down. Say if you have fall off your 500 ton chiller, 2009 that's 0.577 kW per ton. It's actually almost the same in 2012. And if you go with the optional, you're down to 0.57 kW per ton. Now these are all ARI standard conditions. There's an equation that they give you in the book for figuring out what your required kW per ton is for your different, if you're not on your ARI conditions. And you need to make up a little spreadsheet for that, because that thing's quite an equation. It goes up to the cubic power of the lift and the differential temperatures of drawing through that thing. So overall, your cooling percentages, improvement in efficiency compared to the 2009 code, your DX is 5 to 34% more efficient. Air-cooled chiller anywhere from 0 to 11% more efficient. Screw or scroll is 2 to 5% more efficient. Water-cooled centrifugal 0 to 10% more efficient. Okay, we'll talk a little bit about heating equipment. Heating equipment had actually not much change. The basic gas furnaces and boilers are pretty much the table's the same for the basic required efficiency in 2012 compared to 2009. And most of those boilers or furnaces are pretty much around 79 to 80% efficient. So no big surprise there, but if you do go, if you want to use your optional high efficiency compliance path in 506, then you have to go considerably more efficient, have to get like 90 or 92% from gas furnace, and 89 or 90% for boilers. So you're pretty much going to have to look at a condensing boiler if you're going to go with that optional path. Economizer, this is one of the biggest changes that the International Building Code made. Economizers were not required in the 2009 code. Now they're required for all systems over 65,000 BTUs per hour. So that's anything obviously over a 5-ton unit. So now you're looking at, even if you had a 6 or 7.5 ton package unit or split system, you'll be required to put an economizer on it. Your only options there, you can put an air side economizer. If you're in a building with cooling towers, you can put water side economizers. But even with your water side economizers, there's a requirement you have to be able to fully cool your building when the outside condition is 50 dry bulb and 45 degrees wet bulb. Now 45 degrees wet bulb, you're only going to be able to use that to cool your chill water directly off the cooling tower. And that's going to be difficult because if you have like a 7-degree range on your cooling tower, you can maybe get your chill water down to 52 degrees or 54 degrees. So you're going to have to be looking at trying to cool your building at 54-degree chill water, which is going to be pretty tough. Just a note here, your economizers don't have to be entropy type. Seems like everyone's going with entropy type since when you're running through your computer program, and if you're doing a lead building, you kind of go toward the entropy most efficient, and can be the most efficient. But there was a good article recently in Ashford Magazine, November 2010, why entropy economizers don't work. And the basic point of that article is that your humidity controls are really not that accurate. They tend to degrade over time. And when you consider the cost of the entropy control, they're often really not worth it. And the authors of that article came back and recommended using dry bulb economizer for a type of climate. And they said it worked just about as well and be a lot less costly and a lot less prone to error. Now, another big thing affecting air handler design is the fan power limitation. Again, we did not have this in the 2009 code. It's new. The IBC brought it in to the International Energy Conservation Code. It's been in ASHRAE 90.1 for several years, but this is a pretty tough code on the limitation of how much fan horsepower you can have for your air handling system. And each HVAC system has to comply. You can use a couple different methods, the brake horsepower method or the motor nameplate horsepower method. And the fan system horsepower limit is for the sum of all the fans in your system. So it gives you a horsepower allowance, but that horsepower allowance is for the sum of the supply fan, return fan, exhaust fans, and the fan power boxes. So when you really realize that you only have one number that everything has to fall within that, it's pretty tough. These are the equations that they give you, and you can see for a constant volume system, if you use the motor nameplate method, you got 1.1 horsepower allowance per 1,000 CFM. If it's variable and use the motor nameplate, you're allowed 1.5 horsepower per 1,000 CFM. Then if you, alternatively, if you use the brake horsepower method, the second row down there, you're given less allowance per 1,000 CFM, but you are given adjustments for the pressure drop. You're allowed to add some pressure drop adjustments for filters, return ducts, sound attenuators. So you may have a little more flexibility there. So we're going to go through some examples. If you have, so the first two examples are going to be a 10,000 CFM constant volume system, pretty simple system, but with supply and return fan. We're going to say no exhaust fan over 1 horsepower, because exhaust fans, 1 horsepower and lower don't count toward the fan power limitation, so you can ignore them. So if we have a 10,000 CFM system, this would basically give us an allowance of 11 horsepower. That's motor, nameplate, horsepower. So your supply and return fan together has to be less than or equal to 11 horsepower. So you could maybe have a 7.5 horse supply fan, a 2.5 horsepower return fan, and that's it. Now, if you use the brake horsepower method for that same system, this is a simple system, plan and return. If we only have minimum filtration, there'd be no adjustments for the filter adjustment factor. So this would give you allowance of 0.94 times 10,000. You'd have 9.4 brake horsepower allowed. So if your supply fan was, for example, 7 brake horsepower, then your return fan could only be 2.4 brake horsepower, and that would be it. Okay, in this example, now we're going to go with a bigger system, a 30,000 CFM variable volume system, inductive return, runner of 13 filters, also throw in a 2 horsepower exhaust fan, so now we have to include the exhaust fan in the fan power limitation. So if you use the motor nameplate method, you allow 1.5 horsepower per thousand, so you're given allowance of 45 horsepower. If the supply fan is, say, 30 horsepower, then the return fan can only be 10 horsepower because you got to throw in a 2 horsepower exhaust fan. So that would be the limit there. Now, if we use the brake horsepower method with that same system, the 30,000 CFM, we now get our pressure adjustments. And for the North Carolina code, which is slightly different than the ASHRAE code, you're allowed 2 inches for inductive return for that size system. You'd be allowed 0.9 inches static for the MERV 13 filters. So you have a pressure allowance of 2.9 inches. That gives you an additional horsepower allowance of 21 brake horsepower. Your basic allowance is 1.3 times the 30,000, so you have 39 brake horsepower plus 21 gives you 60 brake horsepower allowance. And then again, you have to divide that up between the supply fan, return fan, and exhaust fan to keep it within the allowance. I've seen some code forms on some plans that say, what's your supply fan allowance and what's your return fan allowance? But there's not a separate for the supply fan and return fan, it's all together. So your overall effect on your air handling units, you're going to have, in most cases, air side economizers. With your air side economizers, you're going to have return or exhaust fan, you're going to have larger intakes and leaf louvers. You have to have the control dampers for that and the control system. Then the fan power system is going to affect you because you really got to reduce your static pressure in your system. You need to reduce the external static pressure in your ductwork. You need to reduce the static pressure losses within the air handling unit itself. And we are now designing some systems and we're going as low as 250 feet per minute on a cooling coil. So if you used to 500 feet per minute on the cooling coil, you're now talking about an air handler that's literally twice the cross section, twice as big, in order to get that static pressure down so that you can get within your fan power limitation. And of course your duct system, you need to really keep it low velocity. You can pretty much forget a high velocity duct system anymore. It's just not gonna get it. Now, then there's this section 506 in the North Carolina Code. And you have to go through all your prescriptive stuff, but then at the end you have to do one more additional compliance spec. You have these 6 items, you only have to do one of them. And all out of heart failure when we first read these things, and what you might have to do all of them, but you only have to do one of them. And probably most people are going to be one of those first 2, either use the more efficient mechanical equipment or the reduced lighting power density. Those are probably the easiest to do in most systems. The other ones are a little more specific to your system. But the other ones are, you can use energy recovery ventilation system, even if it's not required in the prescriptive part. You can use high efficiency service water heating for certain types of buildings. You can use on-site renewable energy, or you can use an automatic daylighting system. So the more efficient mechanical equipment, you have a whole separate table for your efficiencies for mechanical equipment, covers all the usual equipment, unitary, PTACs, heat pumps, furnaces, boilers, chillers. So you'd have to go to the other table and use the efficiency out of that instead of the basic efficiency. For the lighting power, if you want to use the lighting power, compliance tab is just simple. You just have to knock 10% off your lighting, your basic lighting allowance for the building. Then some of the other methods, you can use an energy recovery ventilation system. It's specific to certainly you have to have a building with at least 500 CFM of outside air. You have to provide energy recovery for 50% of the ventilation air. It has to be 50% efficient on entropy recovery. So basically it's got to be heat wheel or something else that can use both sensible and latent heat recovery. You can use high efficiency service water heating for certain types of buildings, hotels, hospitals, restaurants, residential buildings, buildings with laundry. And you can either use instantaneous fuel system, heat pump water heaters, geothermal heat pumps, or solar water heat. Your on-site renewable energy, you can either provide 3% of the annual energy of the building. Of course, that would have to be an energy model calculation. Or you can provide 0.5 watts per square foot of building. So if you had a 50,000 square foot building, that would be a 25 kW solar array. Or you can use automatic daylighting control, and you have to provide 30% of the building area with daylighting controls, dim down the lights when you have enough daylight. There are a number of glitches in the code book when it came out, and so I'd like to alert you to some of these. In the high efficiency section of the code, that's section 506, where you have your extra more efficient equipment, on the chiller efficiency requirement, they got the headings swapped for the full load and IPLV kW per ton figures. So you can pretty much figure it out because, you know, your IPLV is always more efficient than your full load, and every number down in that table is swapped, so you have to swap it yourself. Then in that section 506.2.5 for the on-site renewable energy, they've got a statement there I can't figure out because it says either 0.5 watts per square foot or 175 BTUs. Can't figure out anything where that 170 BTUs, because I don't know if it's BTUs per hour, BTUs per square foot, annual, I don't know what it is. It doesn't mean anything. There's one table just in the regular 503 section of basic efficiency that should be labeled utility apply heat pumps. It's labeled air conditioning, but it's obviously heat pumps because they give you heating efficiency. Now there's also, I kind of got you, there's on your economizer requirement, it says you can have an exception and not be your economizer if you have more efficient cooling equipment. You have more efficient cooling equipment, but it says you can do this in zones 3B and 4B. Well, we don't have any zones 3B and 4B in North Carolina. That's west of Texas. So you can't use that exception for the more efficient cooling equipment. Also then in the section 506 for the boilers, it lists hot water boilers and steam boilers, and it says basically they have to be 89% efficient. Well, you can do an 89% efficient hot water boiler, condensing boiler, but I don't believe there is such a thing as an 89% efficient steam boiler. Maybe if you get some super duper condensing economizer section on it, you might be able to do it, but I don't think that's going to be possible. And that's the end of my presentation, but I'd be glad to take questions.